Okay, hello everyone. So today we will be deriving Dirac's equation, which will account for relativistic corrections to the Schrödinger equation. So the non-relativistic, widely known Schrödinger equation has this form, which fails to account for the relativistic relation of energy, which is given by E squared is equal to P squared C squared plus M squared C to the fourth. And this is just E is equal to the Hamiltonian, right? And this is an incomplete form because we have no account for the rest mass, what the rest mass is, the rest energy is equal to mc squared, right? And the kinetic energy of motion, which is, for example, studied in field theory in electrodynamics, right? E kinetical is equal to mc squared times this term, where b beta is equal to v over c, the Lorentz factor, or whatever you call it in English. Yeah. So the first attempt at deriving a relativistic wave equation, well, not a wave equation, but an equation of evolution for the wave function, was done by Klein and Gordon. So the Klein-Gordon equation, which basically said that E is equal to P squared C squared plus MC squared squared, right? Let's just set it like that. And since the energy operator is this, we have that E squared is equal to minus H bar squared delta D squared. The momentum operator, it is given by IH d dx for a single dimensional, and generally speaking it's IH times the gradient, which for the square would be the Laplacian, right? And so we obtain that minus h bar squared times the second derivative of the wave function with respect to time is equal to minus h bar squared times the Laplacian of the wave function multiplied by c squared plus mc squared times the wave function. So this is just a constant term, and this, just like the regular Schrödinger equation, has the form of a Sturm-Liouville, just with the absence of constant coefficients. And by using natural units, we obtain that we have the second derivative of the wave function is equal to minus the Laplacian plus m squared psi. And by substituting for the D'Alembertian, right, the D'Alembertian in non-natural units, non-natural D'Alembertian, it is given by 1 over c squared, second derivative, minus the Laplacian. And we just move it over to the other side. We get the D'Alembertian. So the D'Alembertian is often called the box operator. Box operator minus m squared psi is equal to 0. It is often, I might have mistook, it might be like this, but it doesn't matter, right? So general form, I think, yeah, it's this for natural units, where psi is the wave function. And the problem here is that we have a second derivative with respect to time, which Dirac did not like, right? And so Dirac said that we might need to have a space-time wave equation, space-time equation of evolution, which is first order with respect to time. So what we do is we take for the relativistic Hamiltonian typical expression, which is c, speed of light, times p plus mc squared beta, such that the coefficients alpha and beta have dimensionality equal to 0. And this essentially says that they're just dimensionless constants, such that not to ruin the relation which the Hamiltonian should obey in space-time. And c being constant also basically does not interfere with this, but yeah. And the Hamiltonian, it is known that it is a Hermitian operator, right? Which means that it is equal to its conjugate, meaning that H will equal to H dagger, which is equal to C alpha dagger P plus MC squared beta dagger, right? From here, we derive that alpha is equal to alpha dagger and beta is equal to beta dagger. And the energy of motion, as we have written by the relativistic relation, is equal to c squared p squared plus mc squared squared, right? From where we get that the Hamiltonian squared is equal to m squared c to the fourth plus c squared p squared, which is equal to m squared c to the fourth beta squared plus mc to the third, I think, beta alpha plus alpha beta. We do not concern ourselves with the commuting relation for now. Plus 1 over 2 c alpha. Yeah, let's index it with Greek letters because I like them better. Alpha mu, alpha nu plus c alpha nu, alpha mu, p mu, which is the momentum, times p nu. Okay, we don't have space, but yeah, whatever. So this term is 1 over 2 c alpha mu. Let's write as a commutator. Alpha mu, alpha nu, p mu, p nu. Right. And from here, knowing that this should match this, we get that beta squared should equal 1, beta alpha plus alpha beta should be null, because this term is absent in the relativistic relation, and the commutator for the alphas, right? So alpha mu, alpha nu should equal twice the Kronecker delta. So, right, we have the information necessary to say that, well, coefficients which satisfy these factors must be matrices, right? So, this means that alpha, the inverse of alpha, mu, will equal to alpha mu. Same for beta. And the trace of beta should be null, whilst the inverse of this relation should be minus beta, right? Because we impose this. Right. From here, we can say that beta is equal to the matrix of the identities, like so. Alpha mu is equal to 0, some coefficient, let's call it, I don't know, k mu, and f mu null, the conjugate of alpha, the Hermitian conjugate will be 0 f dagger mu k dagger mu, and yeah, so k mu will equal to f dagger mu, right? Because this, and k dagger mu will equal to f mu. So from this we can have the relationship that k1 k dagger 2 times k times k2 k3 mu times k3 why am I writing q k1 dagger is equal to minus k2 k1 dagger times k3 dagger times k1 k3 dagger, right? So we have a matrix of dimensionality 4. Well, not dimensionality, it's size, so it's 4k, 4n, let's say, right? So it's 2n by 2n. And if n is equal to 1, right? So if we are operating in space-time with 4 coordinates of 3 coordinates of space and 1 coordinate of time, we have the relationship that the Schrödinger equation basically turned to be this plus beta mc squared psi, right? We will not dive into the spin or formalism for now, because for now, in a sense, that is relevant, right? For the goal of deriving the equation itself, because it can be done without spinors, right? And the fact here is that we are operating basically in an abelian group. So, for example, it does not matter where we put c or mc squared, right? Because those are constants, and hence it does not matter the order of operations, because we're so the beta, I mean the alpha here, the alpha matrix. Thing is that these two quantities, right, f and k, they represent submatrices, right? They themselves are matrices. And it can be shown that these submatrices are in fact Pauli matrices. So alpha mu, for example, will equal to 0 sigma mu 0, right? Since this relationship holds. And hence we have a very, very interesting thing, because Pauli matrices, they basically signify spin, right? And this is why, for example, the Dirac equation so naturally governs fermions, right? Fermions, particularly electrons, because, well, one of their main characteristics is their spin. Another way to derive this equation is through Clifford algebra, and basically Clifford algebra is done without relationships here, just implicitly, right? And the Dirac Lagrangian, for example, it's in the spinor field, is given by I psi bar times a gamma upper mu, so contravariant matrix, times dx mu psi, where psi positive is a spinor, right? One, for example, whale spinor is given by this form. So one have spins, like for example 1 2 0 0 1 2, right? This is a whale spinor, and this is the conjugate, and this is basically the fermionic field, but whatever, right? The Dirac gamma matrix is used in our initial calculation, because that's what basically alpha is. So just by using this Lagrangian, we can vary it with respect to the field. So we'll have the Euler-Lagrange equation for fields. So I hate this notation, but what can you do? It's equal to 0. This term is equal to 0. This term yields precisely the Dirac equation. Yeah, so we're operating in natural units. Right. Yeah, that's basically it. That's all I wanted to do.